How are you guys? Please, who knows when is the makeup exam for the midterm? Who knows? I don't know. Guys, seriously, does anybody know when the midterm makeup is? I'll ask Jihan Hoja. He's also very, very busy, so he may not have had time to email you guys yet, but we can ask him. So being at home thing is very distracting. Okay, but yeah, we'll ask Jihan Hoja what time when the midterm is going to be. Okay, send me an email or send Jihan Hoja an email. That's even better, and ask him when the midterm makeup is. He's the one who arranges those. Okay. Good, thank you. How are you? right, right. Okay. Okay. Hello, guys. How are you? What I'll do is I'll share the screen. I didn't know exactly what to do today, but I thought it might be fun to go through some real-time systems since I did so much communications. Yeah, right. I have another class after this, so I don't know. Let me pull you guys over here. Yes, that's better. And just to close this. Okay. So I found these slides. I'm sorry, I'm just like finding slides at this point, but these ones are good. And I haven't taught real-time systems for, I did teach it once, but I haven't taught it in a while. And if you ever get the chance to learn it, 2010 is a little old for these slides, but the principles are the same. I'm going to give you a general overview. We actually teach, there's a real-time operating system, RTOS, which is used a lot for robotics applications. We have a graduate school class, which people teach that. We've had 2 instructors so far teach it. So it's a good. So yeah, I found his stuff on the internet. So apparently he found his slide on the internet. So there you go. We're all copying from each other. So one thing, I'm not sure if I finished the slides from last time. Let me actually see. I got my old class open here. Okay. Let's go to 2020 teaching. I think I finished the slides. I forgot to look before I came in. Presentation 2, I put that up. There was some stuff about noise. I think that's the last thing we did last time. Yeah, I put some notes about noise. You might be interested in it or not. I didn't put yeah, we didn't look at this. I wanted to show you guys, what did I say about the signal to noise ratio? So in communication, really, this is just the gist of communication. In the end, it usually boils down to errors, right? I'm sending 2,000 bits. How many errors do I have in those bits? If I have too many errors, if I have a couple of errors, I can correct it. There are numerical methods where you can fix that. But if you have too many errors, then you lose the packet. The transmitter has to send it again, and it just wastes time and energy, right? So what does this depend on? This depends on the signal power versus the noise power. If your signal is too weak, then you can't even detect the signal. So that means that the signal to noise ratio is too low. But if your noise power is too strong, you have a really noisy system or interference, you're next to a motor or something, emanating all this electromagnetic interference into your band, then your noise power will be high. So this ratio, in communications class, I derived this to show why the probability of error depends on signal to noise ratio, but it definitely does. When you do experiments, you'll get curves like this. Signal to noise ratio on the bottom in decibels, and the probability of error on the y-axis. And this is a logarithmic axis. I don't know if you've ever seen this before. If you look here on this axis, you'll see 10 to the minus 4, and then 10 to the minus 3, and then 10 to the minus 2, 0.001, 10 to the minus 1, and 1. And notice that the distance between these is the same. Now that doesn't make any sense because the distance here is like 1 or 0.9, and the distance here is 0.09. Okay, the distance here is 0.009, but when we show them on the graph, we're plotting them as if they're the same. We're actually plotting according to this exponent, right? The log, this is like minus 4, minus 3, minus 2, -1, and then 0. That's the distance we're plotting. The reason we do this is that when you look at probability of error, you usually, okay, the maximum probability of error, by the way, what's the maximum probability of error? It's 0.5, right? If you didn't know anything about what was being sent and you just randomly guessed zeros and ones, right? You just guess 1 every time, right? You will still be correct half the time, right? 50% of the time. So this is the maximum error is 50%. But these things I'm not really that interested in. I want to see how it's changing, but I don't want 10% error. It's too much. I want something down here, 10 to the -5. To be able to see detail in this range and also see some detail in this range, it's better to have a logarithmic y-axis. The x-axis here is also logarithmic because we use decibels. When you're looking at decibels instead of a ratio, it's basically 10 log 10 of whatever this thing is. Generally, well, I was talking about this generally, but I'll just, this concept is going to come up for you in electronics classes, in any kind of systems classes. So let me quickly do the input-output thing. So you'll see this in electronics. Maybe it'll help you a little bit. Okay. So here, whenever you have a system like, oh dear. Okay. Imagine this is a network. There's resistors, capacitors, whatever. You apply to this an input voltage, Vn. And then you observe at the output an output voltage, often across a resistor, Vout. We are very often interested in what Vout divided by Vin is. Okay, so this is the kind of thing. So signal to noise ratio is not Vout divided by Vn, but it's more like I had my nice signal coming in to my communication system, and then unfortunately somebody added some noise to it because of the circuit, and I have Y coming out. So I would look at energy of X divided by energy of N. That's my signal to noise ratio. And I'm very often interested in these. Now, if you look here, it's volts divided by volts, right? And here it's watts or joules divided by joules. No matter watts or joules. So it doesn't have a unit. Those units are going to disappear. Now, we often look at the result in decibels. Why? It just turns out to be convenient, honestly. When they look at systems, a lot of input output. So what they would do is plot, give input with different frequency, F, and then plot V out versus V in. And often it looks kind of like something like this. This is the plot of V out divided by V in. Or maybe it looks constant. I don't know. It depends on the application. Or sometimes it'll look weird, like something like this, or whatever. Like there's different things that can happen. But we are often interested in V out divided by V in. So what they started looking at here was 20 log 10 of V out divided by V in. And this is the ratio in decibels. Basically, you're taking the logarithm. For the same reason, we take the logarithm, we plot the logarithm in the probability of error, just because it looks better on the plot. That's the whole thing. Now, if you're looking at the ratio of voltages or currents, then you will use 20 log 10. If you're looking at a ratio of energy or power, the formula becomes 10 log 10. Energy of X divided by energy of N. Now, I put big N here, but what I mean is the N. Okay, and this is called the signal to noise ratio in decibels. Now, why is it 20 over here and 10 over here, right? So I don't know if you've seen this in, so you guys still haven't taken circuit classes. You learned this in circuit classes, but you may have seen this in high school. When you looked at the power that was used up by a resistor in a circuit. You remember what this was? This is, let me not draw a square, I'll draw you the little zigzag resistor. When you start taking circuits classes, you won't use this. You'll use a square because it's annoying to draw this all the time. R and then V. Do you remember the energy, the power consumed by the resistor? So remember, the current here is I, and we have a rule that says V is equal to I times R, right? Have you guys seen these? High school? Yes, right, in high school. So, okay, good. Not totally off. And the power consumed by R is P is equal to V times I, right? But because V is I times R, you could say this is I squared times R, and it's also equal to V squared divided by R, right? So this square is the reason for this 10 or the, so what we want to do is when we're looking at the decibels, we could express the property of this system as output voltage divided by input voltage, or output power divided by input power. And regardless of if we're measuring power or if we're measuring volt, we want it to come out to be the same number of decibels that describes the system. So that's the reason for the rule. So if you're looking at a system, and again, there's no resistor here, but imagine that there's this whole system, and oh yeah, this connected, this is what you usually do with systems. You connect it to some kind of output resistor. That's called your load resistor. Okay, just to measure it, even if you connect a voltmeter to the two outputs of the system, like imagine this is the thing with ground and the other probe goes into the volt, right? Your voltmeter has a load resistance. It may be very high load resistance. They'll make it so it's only drawing a teeny amount of current, so it won't affect the circuit inside, right? But it's still a resistance. So that's the load resistance you're measuring. And of course, your input, whatever it is, also has some form of resistance in it. There may be an input voltage that you're applying, say V in, and then there'll be like a resistance that belongs to that circuit, okay? But that doesn't matter. So let's suppose this is V in directly. If this is V in and this is V out, okay? So we may be interested in V out divided by V in, or we may look at the power that's going in, out divided by the power that's going in. We express this in decibels as 20 log 10 of V out divided by V in. And we express this in decibels as not 20, but 10 log 10. By PN. Okay, because power is V squared R, right? And we kind of, in communication, we assume all the resistances are 1. Okay, that's our secret. Don't tell the electronics people. They would hate us. But it's just, we don't deal with resistances. Somehow it will take care of itself. Because when we're transmitting across the channel, and the channel is always attenuating in some way. And your system amplifiers, you can't really automatic gain control on many amplifiers. Oh yeah, I'll give you an example of them. V out squared, I wish I had prepared this better. V out squared times R divided by V in squared times R, and the R's will cancel. Okay? And this is 10 log 10 of V out divided by V in squared. So do you remember what happens when you take the logarithm of something squared? The way the logarithm works, this will go over here, right? So it'll be equal to 20 log 10 of V out divided by V in. Yeah, exactly. 2 goes out, and then you have 20 log 10 V out divided by V in. So this is the correct way to express it. And the same thing applies to current, only it's kind of inverted. If you had only the currents, you would have to calculate 20 log 10 of I in divided by I out, okay, just for it to be equal to this. So that with the current, it's even more complicated. So we don't usually do this. Why would you measure current? It's too hard anyway. Voltage measurements are easier. So yeah, if you measure voltages, if you have a ratio of voltages, volt divided by volt, you should use 20 log 10. If you have power divided by power out divided by power input, you should use 10 log 10. Okay, so example. Suppose I have a communication system where the input signal has SNR equal to, let's say, 10 dB. If the signal power is 1 milliwatt, what is the power of the noise in my input signal? I'm quite literally teaching 3 different classes right now. dB means decibel, what I showed up above. I actually have a nice handout from Analog Circuits about this. I'll put that up as well. They give more explanations, okay? But dB means decibels. So this will come up in many classes. It comes up in communications, also in circuits a lot. But communications, this is how we look at it. So 10 dB is 20, oh, I'm looking at power, right? Okay, so 10 log 10, okay? Yeah, thank you. 10 log 10 of the signal power, which I said is 1 milliwatt, divided by the noise power, which I don't know, okay? And the rest of it is easy. 1 equals to log base 10 of 1 milliwatt divided by noise power. So 1 milliwatts divided by noise power is equal to 10 to the first, which is 10, right? So that means the noise power is equal to 1 milliwatt divided by 10, which is 0.1 milliwatt is the noise power. Okay? Yeah, that's what I'll ask. I'll give you a little bit more. Often, we don't just look at a single value. Often, when you're looking at in circuits classes, what you will look at is you will look at different frequencies. And like I said, across frequency, you look at how V out divided by V in changes. Yes, it's always log 10, yes. This 10-20 thing is just because of this, what I explained here. Because I want to find the same result if I find the ratio of voltages or if I find the ratio of powers. I want to get the same output for the system, the same number for that system. Okay. Okay. So anyway, we did decibels. I think this is quite good in between. So you'll see way more of this once you get to your circuits classes, particularly electronics classes. If you're in, I think mechatronics also takes electronics, which I think is a good thing, and I'll get to that in a little bit. You still have it. I still have all your stuff in. Let's write dB here, and I'll put up another document. That's just the other one I'll put on the website. Don't think you have to study that for the exam. That's just mainly for your interest more than anything. Okay. So anyway, so this is what we looked at last week. Was communications. And these might be like where I got most of the codes from. This one is flat out somebody else's code. So I thought we'd go to embedded systems. Oh, okay. For the mechatronics people, I was like, I wanted to do this, but I don't have time anyway, and it's not my field. But I wanted to show you why do you take so many math classes and circuits classes. One of the reasons is this. Look at this book. It's a robotic modeling and control. Look at the math. Okay, so you think you're just going to be working with robots, but when you get down to it, what we do is we write a lot of equations to figure out how they work. So you use matrices mainly. Okay, so that's math 3, right? Just to show the rotations and model rotating in 3 dimensions, you use these. You know, sometimes it's more dimensions because they add dimensions for how you saw that arm. It moves this way, and then it moves this way, it moves that way. All the different rotations of the axes are on the internet. I can't legally give you any books, but I'm sure you'll figure it out, okay? Get in trouble for that kind of thing. But yeah, exactly. This is a PDF. But there is a copy, I believe, in the library. And this is not very difficult to find. Also, the school has some kind of yeah, sorry. Okay, so the school has some stuff there as well. They have some subscription to ebooks as well. I think you can find a lot of stuff. I also buy used books from. There's online used booksellers, and they actually sell a lot of textbooks as well. But you have to watch out. Some of them are really expensive. But if you buy something that's 5 years old, you can buy cheap books that have the same topics most of the time. This book is very old. This is at least 5 years old. But if you're just learning the fundamentals, it's not that bad. I was going to show you chapter 5, where they go into differential equations. Okay. Let's see. So a lot of the time, what you do is you take your system and you have to model it as some kind of mathematical equation, and it's just you'd be using norms and all kinds of mathematical stuff. So watch out for your math classes. If you are good at math, you will become quite good at this. It's a 5.51, 5.56. There was somewhere there was a gradient. There you go. This is where we get to differential equations. Okay, because you're talking about volatile. We're talking about acceleration, motion, velocity, all those things. I'm sorry, I'm currently teaching in the living room, so it can be a little noisy in here. Okay. Yeah, so you can see, yeah, look at this differential equation with all of these parts, right? So you're going to be doing a lot of math. Watch out for the math classes and the signals classes, because in signals also we learn how to make this into a difference equation and then solve those difference equations, right? So signals classes are actually kind of an extension of math classes in that sense. It's honestly, a lot of the time, a lot of this is not just for motion planning, but to do things very efficiently. Like, it's not good enough today in engineering just to get something done, just to get the car moving. You have to have it move efficiently, so it doesn't use too much fuel, so it doesn't create too many, oscillations in there. Same thing with your circuits, right? You have to have a very good, efficient cell phone, so it doesn't run out of batteries all the time. So how well you do your circuit works, how well your mechanical system works is very important. And for that, you need to do these kinds of optimizations to study exactly where the energy loss is happening and so on. Yeah, so this is why we have so much fun. There's actually a gradient somewhere. I was going to show you guys that, because gradients usually you don't see anywhere outside of electromagnetics class. Oh, there we go. No, next, not that gradient. Okay. Anyway, there's a lot of stuff that you'll be using that's mathematical. Okay, so it may not seem like that, but these are it. Yes, what I'm trying to kind of get across to you is not that difficult. Honestly, if you do it slowly and bit by bit, anyone can learn this. It's not it's not something which is undecipherable, but you can't decide in your 4th year, okay, now I'm going to do this robot control stuff. Let me pull out my linear math 3 linear. Oh, look at this book. What do you need to know? You need to know how to solve these matrix equations. Oh no, that was math 3. Okay, pull out the book for math 3, start studying. And then you're like, oh no, now I need to have a differential equation. Oh, how did we solve these? Oh, let me remember math 4. right? So try to study these. I mean, realize that they have actual applications in engineering. Signals has actual applications in engineering. And if you want to do something which is quite complicated, where you're looking at the motion of a robot or looking at the circuit that controls that, or the software that controls that. I had another one with software, I ended up not pulling it out, but you know, there's a book on embedded systems. Do you know what embedded systems are, by the way? Gömülü sistemler, right? Embedded systems are basically what we're going to talk about, which is a system which is a real-time system. It's a system that works on generally on machines in either factories or in cars, these kinds of things, where they have a component which you're using. It's not like a screen or anything. No, don't get anxious. Don't get anxious. But what I'm saying is study for these classes. The first 2 years are your introduction to these topics. And very often, nobody tells you you will need these later, right? So you're like, well, when are we going to get to the good stuff? Right? And it's okay. Like you can study these later on as well. But it's your advantage to really keep up with your schoolwork in your math classes, the classes that don't seem very boring. Yeah, it is fun. Yeah, it is actually fun. It will get to be fun when you study and then you're not lost, right? In class, it's really hard. I've done that in classes in college. Not all my classes, but one or two where I lost the thread and I had no idea what was going on, and it's very boring and very just demoralizing when you're in that situation. But there's always a book for the class. Go read the book. That always helps. Do the examples, do problems from your books, right? Don't do the homework yourself, and then on top of that, go and do extra examples from the book. That will really help. Very often, at least with my Turkish students, but with all my students, I find that you're supposed to work a little bit harder than you think you are supposed to work. You're supposed to do a little bit, few more examples. Try to find those examples and do them, because it seems like this is very theoretical stuff. It won't have an effect on what you're doing. It actually trains you to think in a certain way and to approach problems in a very systematic way. And of course, if you actually get to do development work and research and development, which probably the most fun thing to do as an engineer, then you need to be good at math, to know how to do these things. You can't just wander into a job and learn all this from scratch, right? That would make it hard on you. So learn that math, learn that physics, even chemistry. Like when you look at sensors, I'm not going to go through those slides, but I had another set of mechatronics slides where the guy was going through the different sensors. Does this one have it? No, there was one set that was very long. I'll put a link to it. But he was going through all of the different sensors, just the way they work. A lot of them are chemical sensors, right? So study for your classes, and so that you have this knowledge. This is your toolkit. When you come in and you're trying to solve a problem, what you know from the fundamentals will help you to solve problems, because you will approach it and turn it into a problem you can solve by turning it into a mathematical problem or a physics problem in that way. Okay, that's my little lecture. I'm sorry. I wanted to just show you that, just to show you that a lot of the stuff you're taking right now actually has applications. Okay, I wanted to talk about, thank you. I want to talk about these real-time systems. Because some of you are mechatronics engineers and even the electrical engineers, a lot of the time you will be working on something which is has hard constraints. If you're interested in automotive industry, avionics, many of those embedded systems applications are real-time systems. Real-time systems, well, this will show you what real-time systems are. Embedded systems in general are used a lot. An embedded system is a computer system that performs a limited set of specific functions. Now, Raspberry Pis are the ones that everybody uses, right? Or those other small systems. But in truth, they've been getting more and more computer-like every year. But the idea is that you don't have a monitor and a keyboard. You really want it to do something that's more interactive with its own environment. Maybe have more sensors, maybe pick up more information, move something around, right? Have an actuator on it. And real-time systems is a system where the correctness of the system depends not only on logical results, but also on the time in which the results are produced. If this is a car with the brake pedal, right? You have to, when you press the brake pedal, that car had better stop, right? If it stops later on, that's no good for us. The car can't give a blue screen, right, of death, right? The car can't crash or break down. Like that would be a catastrophic result if you're on the highway. So there is a time interval during which this thing must occur, and it's very important that you meet those time intervals. So yeah, cars, airplanes, any type of system where it's moving, a machine, any machine that's moving in a factory floor, right? That can be dangerous to other people. Okay, so real-time embedded systems, nuclear reactor control, flight control, basically any safety critical system, GPS, MP3 players, mobile phones. Those are not safety critical, but when you press a button on your MP3 player or your phone, you want it to work, right? Real time, there's no MP3 players anymore, is there? We should take that out. Real time, but not embedded, stock trading systems, Skype, Pandora. With the stock trading, I'll tell you, in the early 2000s, when they first set up the networks, and more people were doing online trading of stocks. In people living in Manhattan, certain offices, back then, getting fiber optic cable to your workplace was very expensive. And most people didn't have fiber optic cable directly to the place, but some of those trading companies had fiber optic cable installed in such a way that basically they were directly connected to the stock exchange. Whereas other companies that were slightly further away had went through a router, I guess, so they weren't directly connected. And there was a time where that made like a price difference, because they could make the bids a fraction of a second earlier than the people in the other trading company. So they were making more money, right? So stock trading systems are real time, but they can be very real time. That communication advantage was huge at that time. Now they have other systems in place, so it doesn't work anymore. Skype, you guys don't know what Pandora is. Anyway, Netflix. Right, so these are also Netflix, YouTube. These are all real-time systems. They're not embedded systems because they work on computers mostly. Embedded but not real-time. Home temperature control, sprinkler system, washing machine. If this was like 3 minutes late, it wouldn't be a big deal, right? Although, when you press the button, you want the washing machine to work as well. So there's some time pressure on it, but it's not hard to meet as well. So event-driven, and they're reactive generally. There's something happening, and the system reacts to it. There's a high cost of failure. So if the brakes don't work, that has a huge cost. There's concurrency and multi-programming. So it doesn't just do one thing. If it was just the brake pedal, like the old cars, was just connected to the brake system's just connected to the pedal. It was just one thing. That's easier because you can just fix that, like the washing machine. But generally, this thing does more than one thing. It's kind of there's a CAN bus on the car, and the brake signal actually goes through there, and so does in modern cars, and so does like the the stuff that controls the richness of how the fuel is being mixed. There's different signals that go over the CAN bus as well, but there's more than one system operating at the same time. The standalone continuous operation, you're not receiving updates to this very often. You just press buttons, right? You're not playing around and fixing the code on the car. Reliability and fault tolerance requirements. Like, things can go wrong, right? First of all, that brake pedal had better work all the time. Has to be reliable. And there's also some fault tolerance. If something happens, you want the car to safely come to a stop, perhaps, or just not break apart. Like, if something goes wrong, it has to make sure that it breaks in a way that won't hurt the person driving it, the person in the car, and also people outside the car. And there has to be predictable behavior, because that's what people in the car are going to react to. They expect the car to work in a certain way, and they base their own decisions on that. So it's a problem if it's not predictable. Okay, so definitions. There are hard real-time systems and there are soft real-time systems. A hard real-time system is where the deadline is very important. Flight control, brake pedal. Right? A soft real-time system is, well, there are deadlines, but you could kind of miss them and nothing will die, right? So data acquisition systems, for instance, you can miss some of the data. It might be some problems with that. Okay, and they're real-time systems, and again, flight control systems where you're looking at everything is hard real time, and response times have to be very, very short, right? So this is a hard type of problem system to code. And then you have firm real-time systems where a soft real-time, but in which there's no benefit from the delivery of service. Like when you're talking on Skype or video conferencing, if a packet falls, it falls. Like you can't get that packet at a later date and incorporate it into the conversation. That's not going to happen. So if something is late, it's late. It just has to be dropped. A single system may have all hard, soft, and real-time systems. In reality, many systems will have a cost function associated. So these are kind of words, they're kind of fuzzy, but instead of looking at it as words, you can look at it as a cost function. Do they have a cost function? It doesn't have a cost function. And I have another set of slides that has a cost function. It kind of says with a hard, like firm real time, the cost function is like straight and then boom, like there's no benefit to it coming late. And then, if it's hard real time, it's like it's constant and then it goes negative because there's a huge penalty to being late. And you can kind of draw different functions for these. Okay, so control systems are systems where you have a plant, something being controlled, right? And how do you control it? Using what's called actuators. Actuators are just computer systems, something attached to a computer that can do things in the real world. So you could say a screen is an actuator because it displays information for the real world. But usually we talk about a motor which turns, or some other part that operates or moves. Turning on the climate control, the heater in your system, something like that. And a sensor is something that detects something in the outside world, detects temperature, detects light. Cameras are sensors, microphones are sensors, just detect stuff. So you have a real system here, and this is your control, right? So this system, this part is controlling the outside, the plant. This is the system being controlled. And you can affect it through these actuators, which are connected to your computer, and then you can pick up the results of your actions through sensors. Like if this was motor speed control, you could have something turning the motor, right? You could start the motor turning, and then you'll have something like a sensor that observes how quickly it's turning, and that comes in feedback to your system. Generally, the control happens digitally, right? There are some applications where you have a circuit doing this, but a lot of the time you'll have a microprocessor or FPGA doing the actual computation. So you will need to do analog to digital conversion to get your sensor inputs in, to get whatever information from the user into the system. AD stands for analog to digital conversion. Some years for the introduction students I teach that. I'll write this down here. Conversion. And DA is digital to analog conversion. The real world is analog, right? Everything in real life is analog. However, most of our computers and computational equipment and FPGAs and most of the systems that we use are digital because digital is easier to produce. It's cheaper to produce. Like digital systems are great. They're wonderful. Computers are everywhere. You can just buy a computer, a microcontroller of eBay, whatever, and put it on your system. So then you have to get the data into your computer and then get the result of your computation out. So all of these, like Raspberry Pi, all these things have A to D and D to A converters. Okay, and then you work in the digital domain. But the real world is always analog, right? Okay, so this is your simple one sensor, one actuator. The sensor that senses things, and then an actuator that makes things happen in the system. Okay, so this says set timer to interrupt periodically with period T. Each time the timer does the interrupt, what do? get your sensor input, look at it, compute what, if this is doing the right thing, what it's supposed to be doing, and then based on your results of your computation, change change the system using your actuator, right? So this system is working every t second. It could be every t seconds. It could be every t microseconds. It could be every t days, right? It just depends on what the system is. T is called the sampling period. No, there's two. Okay, I would say there's two meanings to sampling. Here, I think what it's saying is it's only getting one measurement every t seconds. Okay, so that would be the sampling period in that case. This is how frequently I'm measuring the output. I'm getting one number every t seconds. Okay, so t is a key design choice. It could be seconds to milliseconds typically. Depends though. I mean, if you're talking about an irrigation system, you're trying to water an area, every hour would be fine, right? That's not a real-time system generally. And then you can have static and dynamic real-time systems. You can have soft and hard real-time systems. We talked about this a little bit. Soft was you didn't care about what happens, and then, well, if it doesn't happen, it's bad, but no one's dying. Right? It's not a big deal. Whereas with the hard real-time systems, you really have to meet that deadline. Right? Static is the system environment is pretty much the same. That could be a machine that's working in a factory. It's always in the same factory. It's always doing the same thing. Right? A dynamic environment would be a car. Everything's changing all the time. Right? More difficult problem there. And then you can have periodic and aperiodic. We'll talk about this in a bit. It actually explains it in the slides. Single rate, multi-rate periodic. You could, like I said, there's more than one process. So some things need to be done every 5 milliseconds, and something else needs to be done every 2 milliseconds. Right? And then with the aperiodic, you may have a bounded arrival interval. You know when things are. So periodic means it repeats every so often, right? But with aperiodic, something's going to happen. I just don't know when. And it could be like a bounded arrival interval, like it's going to happen sometime in the next 1 second, or unbounded. Anyone could come in any time to press this button. Okay, so the longer any embedded system or any computer remains on, the less sure you can be that it's working correctly. Because there's a lot of processes going on inside. If two things become out of sync even a little bit that are supposed to be in sync, it can make the whole system kind of lose its synchronization and not work the way it's supposed to. Just get into a different state. There are people who do this kind of analysis even for like Windows systems to figure out when that system is going to crash. But that's a difficult one. What they always said is after like a certain amount of time, you should always reset your computer. You should reset it, just turn it completely off and then on again so you can go back to zero state. Because the further time elapses, the more difficult of a state you can end up in. Taxonomy. So static systems, task arrival times can be predicted. Compile time analysis is always possible. So you can look at the system before you deploy it, before you put it in the field, and see how it's going to work. It allows good resource usage. There's low idle time for processors. So this system you can optimize, right? A dynamic system, like I said with the car, the self-driving car, right? Arrival time is unpredictable. Don't know when an event's going to happen. And you have static analysis possible for simple cases. Processor utilization decreases dramatically because you have to have extra resources to handle things if everything happens at the same time. Suddenly you get a whole bunch of inputs. You have to have enough resources to handle that. And that means you need a lot of excess capacity. So most of the time, your processor should be idle, just waiting for that difficult thing to happen. In many real-time systems, this is very difficult to handle, right? So obviously, yeah, you can see years of development go into making a good system. And you have to avoid oversimplifying assumptions, assuming that all types are independent, for instance. This is highly unlikely. And this is what we love to do as engineers, by the way. I also teach probability sometimes, and often we say, oh, everything is an independent event, right? But in reality, nothing is independent. For instance, if you own a factory and the robots in the factory, the machines in the factory are breaking down, Like you could say, oh, I'll be fine because they're only going to break down one by one. So every year I only need to buy 2 new machines. But in reality, you get a flood, you get an earthquake, something happens, all of them are going to break down, right? And yeah, that kind of thing. So you have to be careful that everything bad can happen simultaneously, and it often does in real life. Soft real-time systems allow more slack in implementation. Timing may be suboptimal without being incorrect. So this has more of a, if something is late, that's okay. Problem formulation can be much more complicated than hard real-time. Because in hard real-time, you're like, X has to be less than 2. And this where it's more like X should be less than 2 and definitely less than 12, but it's better if it's less. So you have to write a nonlinear equation for this. Two common and uncommon ways of handling non-trivial soft real-time system requirements set somewhat loose hard timing constraints for informal design and testing, formulate an optimization problem. Very often this kind of thing is geared to people, right? Because it's still an issue when you have a communication system with a lag. And people can put up with a certain amount of lag, but it makes them uncomfortable. And where that threshold is for the majority of people is something you can actually measure. Like you bring people into the lab and have them, watch the movie with some time delay and see how bad was this. So they rate it out of 10. And then from there, you try to find a system which says, oh, if it's later than this, then it's going to be a problem. Or find some other way of trying to quantify exactly how bad it is to be late. And formulate an optimization problem and solve it using just mathematical methods again. Okay, hard real-time systems, a difficult problem. Sometimes timing constraints are inflexible, but it simplifies the problem formulation. And each task executes repeatedly. Periodic means each task executes repeatedly with a particular period. Factory, right? Every time he takes the door, puts the door on, puts the screws on, and the cars are coming out at a certain rate. And then you can do some static analysis and match the characteristics of many real problems. It's possible to have tasks with deadlines smaller to, equal to, or greater than their period. So, the latter are difficult to handle, multiple concurrent. So you have, a certain number of tasks have to be done. So the system's coming in, and you have to have 3. Tasks are coming in every second. 3 tasks have to go out every second, but they don't have to be done in 0.33 time. And then there may also, guys, turn off your going on. Okay, so you can also have periodic, single rate, 1 period in the system. There may be more than 1 period. That's the other thing. And there may be 2 different types of events. Like you could have something which is like do this 3 every second, but I don't care when they finish kind of thing. And then you could have something else which is much more hard real time in the same system, right? That has to be done every 5 seconds. And if it arrives in the middle of another task, then which one are you going to do first? Right? Those kind of decisions have to be made automatically by the system. You can't go and make the decisions later on. So yeah, single rate and multi-rate systems, a lot of systems are multi-rate. If they're doing more than one thing at the same time, even in the car, like I said, the fuel control and the brake lines and all of these, they have different different time sensitivities and different periods as well. So it can be hard to handle all of those. And aperiodic is sporadic, asynchronous, reactive, burglar alarm, right? Asynchronous, sporadic, only occasionally do you get an alarm. And it creates a dynamic situation though. And the bounded arrival times are easier to handle. Unbounded intervals are, that's just impossible to handle with, it depends on what the task is. Like if it's something like a burglar alarm, it's easy, right? The alarm's going to go off. But then a lot of things can happen in the interval while you're waiting for the alarm to go off. You know how often those break down, right? The batteries can go off on the main alarm or on any of the sensors. The electricity for the building can go off. You can get an electric spike. So a lot of things can happen while you're waiting for this, while nobody breaks into your house, right? So that's kind of part of the problem, is The system has to work all the time. An example here is adaptive cruise control system. Apparently there's a video. We don't have the video. There's a control system. It's a hard real-time system. You know what cruise control is, right? You put the car at a certain speed, and it keeps the speed steady, and you don't have to press the gas pedal. Right, and there's a multi-rate periodic system. There's a camera and a GPS on this, a low-speed mode for rush hour traffic as well. So it will keep you going very slowly in rush hour. And apparently this is the whole thing. Adaptive cruise control system where there's a brake and a throttle, all those are used. Following distance relative velocity, so it checks with radar the car in front of it, make sure it's the same distance from that car. And vehicle speed sensor that to keep you in the right set speed, close to the set speed. But then if you're getting too close to the car, you have to stop it. Right? And then there's an accelerator to speed you up, and a brake. You can be handling these, and then there's an automatic braking. So apparently this is from patent. So this is an actual system that somebody invented and designed and put on there. And these are all the different inputs. Data acquisition, signal processing is used a lot for capture, digital filtering, video, voice compression, decompression, data processing. So this is for finding distance from something in front of you. This would be used in, sorry about this, just hold on a second. Okay. Response times from a few milliseconds to a few seconds, typically simple control systems. Yeah, in some way, yes, but then nowadays you can see this radar. Okay, thank you for noticing whose mic is on. You can also see that in this, like video capture and radar signal processing today are used for cars, autonomous cars, right? Autonomous cars. That you're trying to, and then digital filtering of those results, you're trying to figure out if there's an object in front of you and stuff like that. So yeah, some of these systems are simple if they're just to capture something unimportant, but sometimes they can be quite complicated as well. Depends on application, depends on what you're trying to do, right? Other real-time applications, real-time databases, stock market, airline reservations. This is almost what we call the big data, right? Big data today is databases plus learning algorithms working together. Okay, so that's the whole big data thing. So the real-time databases themselves can be quite a problem because you have this transaction scheduling problem. And real-time scheduling algorithms often have conflicting goals, meaning that you want to make sure that everyone can make the reservation. At the same time, you want to make sure that there's no discrepancy where two people book the same. Does it sense minerals or objects? Which one? Real-time database? No. You're on the previous slide. This one? Anas, I don't understand the question. This slide? I don't know. He said data acquisition, signal processing. I think he's thinking more in terms of, you know, those video game controllers where it's looking at the camera and some radar. That was in 2010. That was very popular because that's when Xbox first came out with that Kinetics or whatever it was, where you could do, you know, you could play the game by, and they had a controller that had, at the time, they had some kind of radar thing on it that it could sense how far you were. My guess is he's thinking about something like that rather than about autonomous vehicles. Those were also on the radar, but not as much as today. My guess is that's the kind of thing he's talking about because it has voice compression, the video and voice compression, decompression. This could be even like video conferencing, right? And then why would he have radar there? Anyway, it could be different applications too for these. But yeah, I mean, there's many applications today that use video and radar. So yeah, you're right. It could be mineral deposits as well. That is a whole other area because if you're looking for mineral deposits, that is like a very difficult problem in terms of solving locations for things that you're collecting from data. There's, yeah, I mean, people track from space. You can have the you know, satellite pictures and they put those together and figure out which area would have mineral deposits and stuff. That is another signal processing application, but not real time. That can be done offline. Yeah, real-time databases. Databases are a huge problem because you need consistency. Everybody needs to see the same database, right? Multimedia, you want to process audio video frames at steady rates. Other requirements, lip synchronization. When somebody's talking, the voice should be synchronized to their lips, right? Everything else can be delayed a little bit, but that is very disconcerting when somebody's talking and then it doesn't look like they're saying those words. So you want low jitter. If you delayed by a whole second, it's fine. But if the picture just keeps freezing and unfreezing, freezing and unfreezing, that can be due to jitter. The time it's short, and then it takes too long for the next packet, and then the other packet arrives immediately. So your system has to handle that. And you would rather not wait half an hour to watch a movie. So the low end-to-end response time is important as well. And of course, for calls, you do need real-time kind of communication as well. And you see more and more communication systems going into this. And asking, are all real-time systems real-time systems? Well, payroll, generally, we're only interested in systems which it's not obvious how to meet the timing constraints. Like when you're making payrolls, payments, when you're paying your employees. It's pretty easy how to make that system work so that everybody gets their paycheck on time. It's not going to be like scarcity. So it says, really, we're interested in the window of scarcity, resources, meaning computational resources, transmission bandwidth, how much bandwidth you have to transmit your data, maybe abundant, right? And then you don't need to worry about it if it's real time or not. Like it will work out. Insufficient, the application is ahead of technology curve. It just will not work. Like you can't make this thing work. Sorry. Then you have insufficient resources. You can't design a system, right? The real-time system design comes in when you could do this task with these resources, with this computer and this network. You could do it, but you need to think about how to do it. If you're very careful, you can do it. So that's when your design methodology becomes important. You can design the system to do that. Wow, there's a lot more stuff. Let's go back to here. We'll just do a little bit more and then go. OS or not. In the old time, typical embedded system configuration was hardware and then program, right? And this includes things like FPGA systems, where you have the FPGA hardware. There isn't even a microprocessor there. There's just some hardware logic that you can. So we teach FPGA programming. In those kinds of things, you can actually make a computer using the FPGA board. You can make a typical CPU, put the memory blocks in there, so you can build a microprocessor using FPGA. It won't be a very fast one. Like it'll be very expensive for the speed, but it will work. And instead of building the whole computer, usually what you do is you just use the parts you need for your particular operation, right? So there you don't have an operating system on this thing. You just have a bunch of code, or you reformat the system using code in order for it to do what you want it to do. The other thing is you may have an operating system. If you have an operating system, Windows is not going to work. For real-time systems, you need a real-time operating system. Windows is your typical general use operating system. So it'll work, it'll do everything a little bit, but it doesn't have any guarantees that this will execute in so much time and that it will fail in a graceful manner. It could just totally crash. It's just too complicated, does too many things. So generally, real-time operating systems are smaller, and they only do a subset of things. So they won't do everything, they won't run everything, but they will give you guarantees that they're not going to crash. And what is that here? I'm not going to get into the programming then. The Java is used also in real-time operating systems. There's a real-time RTOS, which has become very popular. It's literally called the real-time operating system, right? That's what they called it, and it's probably the most popular operating system that is real-time that's used today, and it's easy to use as well. Yeah, this is generally there's some kind of super loop running all the time. The system's going through this all the time, and the tasks are kind of scheduled in there. Just sometimes, if something is gonna like be event-driven, like this only happens when X event occurs, when we see this reading on the sensor, then that has to be kind of slipped in between the regular routine tasks in the system. And then sometimes you're doing this important task, but then a very important task appears. You might have to stop your important task, do the very important task, and then go back to doing the important task, finish, and then go back to your regular loop. Right? So this is very often the kind of system you're talking about. And then there's a question of, are we going to allow this to interrupt the other task? Is it that important? This is called preemption in real-time operating systems, in real-time systems. Are we going to allow this to preempt what was going on before, or do we wait until the end of this operation? Because it takes, see, what you have to do is you have to store all of the state variables for ISR, the second ISR, in the stack or memory, and then run this, finish, and then you go back and take all of those back out of memory, put them in the right place, and then you can continue operating. So that's what the operating system does. Make sure that the variables for this don't get mixed up with the variables for this. Right? So that's kind of the goal of the operating system: keep everything running and keep them out of each other. Make sure they don't change things, change the same thing twice, right? Yeah. Yeah, we don't need to really say it. Preemptive. I talked about preemptive scheduling. You can stop service, or non-preemptive. Some systems say you can't stop anything. Everything has to finish and then you start again. Or certain things can be preempted, certain things can. No file management, just a simplified operating system. Yeah, and interrupts are generally, when you learn microprocessors, you learn about interrupts. So you can make your program throw an interrupt, and the interrupt is this thing that's getting in there and making sure that it gets executed before the next one. Or this one will throw a second interrupt. And if it's a more important interrupt, then it will interrupt this program that's already working. So that's kind of how this works in real life. There's a lot of programming involved in electrical engineering and mechatronic engineering today, because a lot of systems run on microprocessors that you will need to program. So also watch out for your programming classes. Do code, learn to code, not just during your programming classes. I would recommend that you just learn some coding, whatever you're interested in. Do game programming. It doesn't matter what you do. If you get programming experience, it will translate to another field directly, because a lot of these ideas go between the different fields as well. So yeah, learn programming and watch it. Pay attention to all your classes. Okay, so I think that's all I'll talk about. Does anybody have any questions? No, everyone's fallen asleep. Okay, I'll see you guys. I think we don't have class next week. Do we have class next week? Okay, I'll ask Gianluca what's going on next week. Okay, so I'll talk to you guys later. Okay, take care. Okay, take care. Bye bye. Thank you.